So in this problem, when you do it in your homework, you're going to have to fill in some of the blanks in this chart. You have to do this for yourself. And I've kind of filled them in correspondingly for us with these colors. So if you're looking at the notes later on, you can kind of see what goes where. Some of these things you needed to get by subtraction. That's good. I actually want to start out with kind of a reminder of something we did the other day, and that is the probability of one event or another. And that was this formula, probability of A or B. Now what happened with that probability of A or B? I mean, a lot of people get the first part, probability of A plus probability of B. But then there was a little extra part that we figured out that we needed the other day. Does anyone remember what that extra part was? Minus probability of A and B. Right. Probability of that intersection. So what's going on there is that if you have a sample space and have events, say A and B, if you're looking at the probability of A and B, if you just add them up, you add up the probability of A plus the probability of B, you're really counting this area twice. And so that area is the intersection. It's a probability of A and B is what you're looking at. So because you've counted it twice, once when you calculate the probability of A, once you calculate the probability of B, you subtract it off once. So let's see if we can't figure out the probability of someone who uses marijuana or tests positive. So let's use some notation here. I'll just call that a use, and I need a different notation for test positive. I don't want to use P because I don't have P of P, which T? All right. All right, so what we want to find is a probability that they use or test positive. And accordingly, this is going to be the probability of U plus the probability of T minus the probability of their intersection. Now for these probabilities, we're going to look back at the table. I'll give you a second to copy this down before we look back at our table. Now this is what's called the general addition rule. And it's good to use that even though sometimes there's a little bit of a shortcut. And that shortcut is when we have mutually exclusive events. All right, so let's take a look at the probability of someone being a user. Now, we're not just worried about the users that test positive or the users that test negative. We want the probability that we pick somebody who, in this group, was a user. So what would that probability be? Well, how many people are in this table altogether? 300. So that should be your denominator. Of those 300, how many of them were users? Got to be careful. 122. Well, it just says user. It doesn't say that they tested negative or tested positive. They said they're users. So there's 122 users altogether. So that's the total we should use. So, Michael, you seeing the difference there? That
I was looking at it, it says 3 false negatives. So would the false negative be a positive? That's why I combined.
Now we're just looking at the users here. So if they used, then that's going to be their 122. So there's 22 people that were users. We're not worried about how they tested.
Okay, so we're considering the false negative as a user.
Yes, because they are.
Okay.
Yeah. Now, let's take a look at the ones that test positive. So how many people tested positive? What's the probability that you had somebody that tests positive in this example? Yeah, good. 143 out of 300. Please make sure you put those denominators there. 143 is not a valid probability. Now the problem is you've got some overlap when you do that. If you looked at our table, then let's see, we had the first line across, and then we did another one down, and those overlap right here. So we've had some double counting. So we're going to subtract off where we had that double counting. Now, that subtract off part is the probability that somebody was a user and tested positive. So how many people were in that group? 119. Good. And when you total these all up, you get 146 out of 300. And so that would be our probability that somebody was either a user or tested positive. But this is
on
it.
a test, sorry.
Yes, yeah, go ahead. On a test?
Do we have to like write it fully out like that, or could we just do 122 plus 24 over 300?
122 plus 24 over 300. That's a good question. Let's see, 122 plus.
Because it's your total of users plus the positive of the people who don't use.
I'd probably be happiest to see this. If you wanted to explain it a little bit, I'd be happy because sometimes people get the wrong answer or get the right answer for the wrong reasons, and I get a little nervous if there's not an explanation. My go-to example of the wrong work getting the right answer is this one, 64 divided by 16. Somebody could go, hey, I'll cancel the sixes. 4 over 1. Hey, I got the right answer. Yeah, but it's the wrong work, though. All right. So if you wanted to be a little bit more clear about your reasoning, yeah, I'd take that. I mean, it's not wrong. I see what you're doing. On my answer key, you would probably see something like this. But, if you're clear about your work and your reasoning, I'll give you credit. Now, it is in your best interest to show me some work so that if you do make a small mistake someplace, then, I'll just take off a small amount of points. But if you get the wrong answer, even though, you probably knew what you're doing, I can't give you any partial credit if I can't see any work. So,
Okay, that makes sense.
yeah. Michael.
I'm not tracking where you got the 119 for the minus P.
So, so we're looking for the people who were users and tested positive. So amongst the people we're using, how many tested positive?
The 119.
Yeah, 119. So the probability that we find somebody that tested positive and was a user would be 119 out of the 300.
Oh, okay, I see. So the U and the T aren't two separate numbers. That's what you.
Yeah,
Okay.
yeah. So it's describing a compound event. Both of those things have to happen. Appreciate the question. All right, let's do something that's kind of a lead into section 4.3, which is where we're going to spend the majority of our day. And this is kind of a review of stuff that we did that we did on Monday. So we're going to sample from this table in a couple different ways. One of them is with replacement and one of them is without replacement. Now it feels funny to sample with replacement. It's like, well, why would you want to sample them twice? Generally speaking, you wouldn't. All right. But I'm going to let N1 and N2 represent the event of randomly selected somebody who tested negative on the first draw and then on the second draw. Now, let's try and find the probability that they tested tested negative on the first draw. How many people tested negative on that first draw? Yeah, 157. All right, so 157. Now, if you look at the results of that first draw, and you're like, okay, and you put them back in and shuffle things up, what's the probability that you draw out a second person that tests negative? 157. Basically, 157 over 300 squared. And this is probably the way you would calculate it on your calculator if you had to, rather than type all this stuff in twice. That was sampling with replacement. What's the difference if I sample without replacement? Yeah, for the first one, it's 157 over 300 as before. But then I think I heard a couple voices telling me what happens on the second one. What happens on the second one? You subtract 1 from just the numerator?
And denominator.
And the denominator, thank you. So 156 over 299, and there you go. So are these two probabilities the same? No. They'll be close, right? They'll be pretty close, but they're not the same. So that leads us to this definition down here of independence. Two events are independent if the occurrence of one does not affect the probability of the occurrence of the other one. So whatever happens with the first one doesn't affect the probability of the second one. Which of these two methods of sampling lead to independent events? The first one or the second one? The first one. Because the first one, once you draw this one out and you look at it and you put it back in, the probability of drawing a second one out hasn't changed, right? Here, when you draw the first one out and you don't put it back in, that probability is different. So sampling without replacement, that leads to dependent events. Leads to dependent events. And this one, sampling with replacement, leads to independent events. And that's going to be, independent events and dependent events. That's going to be a little bit of a concern here for us as we work things throughout this course. Now, I'm going to use this more in the next section than I am here, but there's this 5% guideline that's going to make our life a little bit easier when we work on these things, and that is if something has a probability, or if our sample size is less than 5% of our population, then we can treat them as if they're independent. Yes, sir?
When writing our final answer, that the 157 over 300 and 156 over 299, that would be the final answer?
Yeah, I'd be happy if you just left it there. I mean, I don't really see much benefit to me for you multiplying it out.
Oh, no, I get that.
Yeah, yeah. This would be, like I like to say, my inner child would be doing somersaults if you got that answer, right? The problem with you giving me a decimal answer is that these would be really close. I wouldn't know, I'd have to look down like 3 or 4 digits before I could see any difference in your answer. So that'd be a problem there. Whereas if you just leave it like this or this, I can see right away that you've got the right method. Yeah, so appreciate the question. Anything else on this one? I think we got a lot of good use out of example D here. So let's move that one aside and flip over to the back side. I got a couple questions that you can spend a little time with for yourself and or talk to a neighbor. So you've got nearly 16 million adults in a region. If a polling organization randomly selects 1,235 adults without replacement, are the selections independent or dependent? If the selections are dependent, can they be treated as independent for purposes of the calculation? So let me just help out a little bit here. Let's calculate 5% of that 15,958,866. All right. So that'd be 5% is 0.05 times 15. And where is that number again? 958. 866. Awesome. So 5% of that is almost 800,000 people. So is our sample size less than 5% of that number? Yes. Easily. So go ahead and try and take a look at these two and see what you think. Let me zoom in a little bit. Running out of room for my pause button here. I know, I will make a new pause button. Heavy economic investment in this class. There you go.
So, if it's, trying to understand the 5% rule, so if it's,
That's our sample, if that's less than 5% of that, then you can treat them as if they're independent.
okay.
Yeah. You know what a copy room is, right?
Yeah, we're just doing both of them.
I think I sent something there that talks about the 5%. It should be
No, it's not. It's done.
tray.
It's gotta
Oh,
be
yeah,
less
so
than
it's not-
because it's less than 5%.
It's done. That's when we get to.
Talking about the very first one.
All right.
Independent or
But it's done without.
Are we getting a consensus on this? How about the first one? Is the selection, as it is the selection independent or dependent? Not worrying about the 5% rule. Dependent, yeah. If you're selecting without replacement, that's going to mean that they're dependent. Where's, yeah, should have highlighted this one. My bad. Yeah, it's always dependent. Now, is it going to make a big difference in your calculations? Yeah, yes and no. I mean, it kind of depends on the particular problem, but probably not, especially if it satisfies the 5% rule. So if you're hedging your bets on like an SAT or something like that, which two could you get rid of right away? B and C, yeah. They're not independent. So the selections are dependent because the sample size is not small relative to the population. No, that one's not true. Sample size is small relative to the population. It's less than 5%, much less than 5%. Actually, it's probably less than 1%. So the correct answer here is this one. Nice, nice. Yeah. All right, how about the second one? Yeah, please. Hang on. So we calculated 5% of this number. 5% of this was just under 800,000. So let's see. Turned out to be 797,943. So what you want to do is you want to compare your sample size to this number. So our sample size that you're comparing was this one right here. This is less than that total, so we can treat them as if they're independent. So that's what allows us to use that independence. Bless you. Now, let's keep going. How about the second part of this? If the selections are dependent, can they be treated as independent for purposes of calculations? Which two can I get rid of right away? Which two of these can I just say, yeah, that's wrong?
A and B, because it says greater than 5%.
If the selections are dependent, can they be treated as independent for purposes of the calculations? So our answer to this first question here is what? Can we treat them as independent? The answer is yes, so I can get rid of the answers that say no, which would be this one and this one. They're not independent. Thank you. Okay. So which one was our final answer then? Which one works? C. Yes, because the sample size is less than 5% of the population. So Yay. Now, I want to go over this again with you with a different example, and it's pretty much all worked out. I just want you to kind of really pick up the advantage of using independence, even though it might not be technically independence. Calculation-wise, it's very advantageous to do this as if they're independent. So, before I move on from example E into example E bonus material, are we okay with example E so far? Yeah, Therese?
So, for like a different example, or say it's on the test or something like that, when can it be treated as an independent?
If their sample size is more than 5% of the population. So for example, let's take kind of an artificially low number. Talk about the number of people in the U.S. Senate. There's 100 people in the U.S. Senate. If you sampled, say, 12 of them, well, that's 12% of the population, right? 12 over 100. That's more than our 5% rule, so you couldn't treat any calculations as if they were independent. They wouldn't be in any case, but if the sample size is small enough, you can treat them as independent. And that gives us a nice advantage when we can. Okay, and that's a good question. It's what this next handout is going to try and really drive home. So I borrowed the 1,235 from example E, and I imagine this in being in a small town where you're going to be voting on some issue. And of those 1,235 people, 600 of them are in favor of proposal A, the rest of them are against it. Let's see if we can't find the probability that if we sample 5 of these voters, what's the probability that they all favor proposal A? So here's my notation. F1 is the probability that the first person favors proposal A. F2 is the event that the second person favors proposal A, etc. Now, with this kind of sampling, if I'm sampling these 600 people without replacement, then is that going to lead to independent events or dependent events? I got one lonely voice. If you're sampling without replacement, dependent. So if it's leading to dependent events, and I should probably write that here, sampling without replacement, sample without replacement. Yeah, and then it leads to our dependent events. And you see that in our calculation here. If I wanted to calculate the probability of F1 and F2 all the way up to F5, then what's happening every time I take somebody out of this population? Yeah, these both go down. You go down in the numerator, you go down in the denominator, etc. I was literally putting this together right before class, and I don't know, would you be really happy if I made you multiply this all out on a calculator? No. I wasn't interested in doing this on a calculator either. I'm like, you know, that's a lot of multiplication. So I pulled out Google Sheets. I just wrote down these numbers and then these numbers. Actually, I wrote down these, and then the next cell I said subtract 1 from the cell above it. And then I copied that down. And then over here I said, well, divide this by this, and I copied that down. So I did very little work. I was trying to do as least work as possible so I could on this one. Terrell?
Would something like that be expressed as an integral?
No.
No.
No. That'd be for like continuous functions. And then this last cell, I said, well, let's find the product of all of these. And I got this number right here. So is there a good chance that you could draw 5 out of 5 people from this population and have them all favoring proposal A? Probably not. All right. Could it happen? Sure. Absolutely. But let's take a look at what our 5% rule says. So 5% rule. 5% of 1,235 Well, that's going to be, 60 something, I would think. So 0.05 times 1235. Oops. 1235. Yeah, 61.75. Is our sample smaller than that? What's our sample size? Let's be careful. Sample size. Yeah, somebody over there said it. Thank you. Our sample size is 5. We're only taking 5 people out of that population. That's our sample size. That sample size is less than this. So 5 is less than 61.75. So we can use the 5% rule. So use the 5% rule. So what's that 5% rule going to look like? 5% rule is going to say, you know what? We're just going to treat these all the same. We're not going to treat them as if, one's getting smaller, from the next, etc. We're just going to treat them all like this. Now, if I asked you to do all this on an exam, are you going to multiply this and then times this and then times this? No? No? Is there a better way? Yeah, you're going to put it to the 5th power. 600 over 1235 raised to the 5th power. Does this calculation look a lot easier than our other one? Yeah. It's like, whew. Yeah, for a second I thought you wanted me to do actual real work here. All right? No, you're going to use the 5% rule. Now let's take a look at how close these things are in terms of their answers. So if I took just this one and raised it to the 5th power, then I get this. Are these two answers close to each other? Very close. They're within about 1% if you actually took time to calculate it out. So by giving you the 5% rule, the author's trying to make life easy on you. And I kind of like that, all right? I don't really want you having to do this kind of stuff. Even if you had a spreadsheet available to you, it's still a little bit of a pain. It's not a huge pain, but you can take a look at all the work I did for this one versus the work I did for this one. This one is a lot easier. So that's my spiel on the 5% rule. Are we okay with the 5% rule? All right. It's something that you're going to be expected to be used or to use, so do keep it fresh. All right. I always kind of like example F. And I think the numbers, are kind of old here, but they're still probably pretty representative. If the world was a village of 100 people, then they would have the following distribution of blood types. So you've got types O, A, B, and AB. And then within those types, you have positive and negative. And that RH stands for Rhesus monkey, which is where that protein was found. Let's put in a couple subtotals here for ourselves, just so we have them handy. So let's see here. I want to find something small to write with. There we go. So we've got 45 here, 40 here, 10, and 5. So overall, you have a total of 100. Now, I get a little bit lazy here on the marginal totals. I'm going to add up this one this way, and I get 14. I don't feel like adding these up. What's a better way to get this total here? Yeah, 100 minus 14, so 86. Okay, so there it is. By the way, what's the most rare type of blood that you could have? Not O negative. O negative, there's 6 of them. AB negative, yeah. If you're on AB negative, the Red Cross probably knows your name, Big Brother's watching you and say, come on, we need some help. AB negative is kind of rare. O positive, I think they're the universal donor. And then, which one's the universal receiver? Is it, is it B negative? No, it's got to be one of the ABs, I would think. Is it AB negative? Not sure about the universal receiver, but I don't know. For my money, I think I'd rather be O positive because there should be a lot around. There's a lot of us around here. So, just out of curiosity, how many people know their blood type? Just a few of you? Okay. All right. Forgot. All right. So let's take a look at a few probabilities here. Finish things up. Let's start with the probability that you have negative type blood. So it could be O negative, A negative, A, B negative, B negative. What's the probability that you have Rh negative blood? Nice. I'm glad you didn't just give me 14. It's 14 over 100. 14, what would be wrong with 14 in and of itself as a probability? Yeah, it's too high. It's over 1. Probabilities are between 0 and 1. So if you're giving me 14, I don't have to think very hard as a professor to know that that's just wrong. Yeah. So it's not even a partial credit right. It's just wrong. How about the probability of Rh positive and B? So you got to think a little bit carefully on that one. Probability of Rh positive and B. Well, I'll tell you what. Let's do ourselves a favor here. Start out with 100 in the denominator. But now you got to look for where both of those events overlap. So Anthony, what are you seeing? How many people fall into that category of Rh positive and B?
8 over 100.
Nice. 8 over that 100. Okay. Now we did one like this before here today. Let me remind you, this is a probability of this or at. By the way, thanks Anthony. So we want to go back to this one, probability of A or B. How do we calculate that in general? What's the general formula for this one?
Equals probability of A plus the probability of B minus the probability of A plus B.
So probability of A plus probability of B minus the probability of their intersection. So, okay. Let's take a look at this. If you notice, I kind of, led you through this a little bit, right? We calculated one of those probabilities. So I want the probability of Rh positive plus probability of B minus the probability of Rh positive and B. And if you look at some of my old exams, a lot of times some of these questions lead into the other ones so that you don't have to redo things, trying to make it a kinder, gentler test. Now we already know the probability. Well, actually, I don't think we calculated that one. What's the probability that somebody has Rh positive blood? 86 over 100. Good. Probability they have type B blood. Yes, nice. 10 over 100. Minus the probability of their intersection. 8 over 100. Should be 8 over 100. So overall, what's our probability? Thank you. 88 over 100. Okay. And a couple more things here. let's take a look at the probability of A1 and A2. A1 is going to be the event that the first person you draw out has type A blood. A2 is going to be the probability that the second person you draw out has type A blood. And we're sampling without replacement. So give yourself a shot at that. Put down my pause button here.
Like, just type A blood.
Just type A. That's all we're worried about. The first person and then the second person have type A blood. And then there's a question below it that you can answer about which sampling method leads to independent events. No, I kind of wrote past this a little bit. I guess I've given you two calculations. One is with replacement, and the other one's without replacement. So there's two there to do. By the time you make those things, you hardly need them, which is okay. Yeah.
I was learning everything as I was going.
Yeah, good deal. See if you agree with Katie.
Okay.
Okay.
With replacement, is gonna be the square root of the same one. Without replacement, it's gonna be one. So you take one out. No, you got the answers right. Switch the
Oh.
question.
Yeah, that was the other day's.
This is without. No, this one is.
Try and answer
without
it for us.
replacement. This one is
You got all the numbers you
You're
need.
always gonna square with replacement,
Mhm.
because nothing changes.
Yeah.
I see what you mean.
Yep.
Without, just deduct.
You get what you
I was, yeah, I was getting
You
like,
get it. Yeah, you just switched.
so with replacement.
Square.
Square. Yeah,
With
that's the same
replacement,
thing.
square.
I'm turning that down.
39 plus
Replace.
6 or 45.
What's your cheat sheet for? It's huge.
All the principles of accounting.
Okay, all right.
You look like an accountant.
Do I?
You do.
My dad is.
You do. I think it's that.
Is that a good thing?
Yeah, no. It's that.
I just
It's
don't
that
like-
reserve stuff.
I've never like heard
Appreciate it.
somebody
Like
say
the mind,
that.
the gears are always spinning.
Yeah.
I appreciate that.
Okay,
I can say it too. Let me explain it like
so let's take a look at both of these.
I don't think it's
Neve, what'd you get for the first one?
Are you asking me? Did you say Neve?
Yes.
Oh, I got 40 over 100 squared.
40 over 100 and 40 over 100. And you're right, that's 40 over 100 squared. Nice. Now, in the second one, we're still going to get 40 over 100 for the first one, but what happens in the second one?
You take one out from the numerator and the denominator.
Yeah, taking one out from the numerator and denominator. So 39 over 99. So that second probability changed, right? Now, if what happens on the first event affects the outcome of the second event, then they're dependent events. They're no longer independent because what I did here changed what happened here. So these are dependent events. So which sampling method results in independent events, sampling with replacement or without replacement? With replacement. Because that second sample here had the same probability as the first sample. Nice. All right. Are you comfortable with some of these calculations here? All right. Good deal. Good deal.